All right, guys, we're going to start with circuits, and then these are just a rundown of the equations, but we'll run down those as we go through the notes here. Then electric circuits, we're going to do some labs. We'll go through that. So here, what is a circuit? Just a closed path that allows charges to flow. I don't know if you've ever, probably elementary, middle school, messed with just some simple wires, battery, and a light bulb, but you always had to close the loop. It had to go from out the positive end or negative end, out one side of the battery, through the light bulb, like this picture shown here, um, out the one side of the battery, through the wiring, through the light bulb, back into the other side of the battery. That's what we consider a closed path, and then that's what allows charges to flow. And how we describe the charge of the flow of the charges is this thing we call current, and it's just the rate at which charges flow. So I is current down here is just the change in charge over time. And then over here is just a simple circuit. This is a circuit for a cell phone. It's a lot more complex, but the whole idea is still the same path. There's a closed path, and then it does different whatever it needs to do. Measured in amps. So charge is measured in coulombs, and time is measured in seconds. Charge, and we'll talk about charge more, but so it's charge per second, so it's coulombs per second. That's what we call an amp. Then that's current, the unit for current. Then sorry, videos. They'll flag the videos, but if you look up, there's videos on current flowing through light bulbs. You can actually see the filament. Now it has to be a filament light bulb, but you can see the filaments moving, and then that's the electrons actually hitting each other, heating up. Like the heat increases to the point where the electrons release some of that energy as light. Now, what direction do the electrons flow, or charge in general? Charge could be a flow of positive or negative. So there's two ways you can look at this. Electrons are negative, and so if you put a bunch of negative charges near the negative side of the battery, they're going to repel, and that's what the blue is showing. That now charges don't actually flow like this. They kind of jostle around. Over a long time, they'll make it back to the other side of the battery, but it's a long time. Like, it's just a like dominoes falling down. The dominoes don't fly across the room. They move like, you know what I mean? They fall over and they're displaced a little bit. That's what the electrons are doing. They get jostled. So for electron flow, electrons repel each other, right? They're like charges, so they don't want to be near each other, so they repel each other. So the electrons are actually flowing from negative to positive. When we were first studying, not us, but like history, when scientists were first studying charge flow, they just went with it goes from positive to negative. It works, so we never changed it back. So we are going to follow the red arrows, which we call conventional flow, and then we'll just say it goes from positive to negative. Either way is fine, but I'm telling most of the questions either they'll be specific to electron or conventional, or just assume conventional. And then AC DC or DC AC is how I set it up on the slide. So there's direct current and there's alternating current, and then you got four big figures from, I don't remember the time frame. I don't know, 1900s, that kind of time frame. But direct current this is Latimer and this is Edison. And then over here you have Tesla and Westinghouse. So Tesla and Westinghouse were pushing alternating current, and then Latimer and Edison were pushing direct current. So these guys, Edison's money and Westinghouse's money, they don't actually design anything or build anything. They do fund it and kind of like lead it, but they're not the brains. The brains was Tesla and then Latimer. The problem with DC, well, a couple things. It's hard you lose more power over greater distance, so you couldn't transmit it that far without another power station. And then it's not easily converted, or you can't step it up. You can't get more voltage out or less voltage out. Like, what you send out is what you send out without some kind of conversion, but that wasn't easy at the time, so it would have been expensive. And then wireless charging is not possible with direct current. So when you're thinking direct current, you're thinking batteries. Batteries are all direct. The charge just flows one way. Alternating current is what comes out of your outlets, and then it alternates from positive to negative. It has little power loss over great distances, so you can set up a power, and this is what we use. You can set up power plants miles away from the city, and then just wire that electricity into the city. It's easily converted to DC. That's anytime you've like plug in your Chromebook, it has that little box that converts the AC out of your wall to DC battery power that your Chromebook wants. Same thing with your phones. Um, there's some kind of converter between the two. AC, and you've seen these out in neighborhoods. They're up on the power lines. There's these cylinders. Sometimes they're in the neighborhood yards, like they're green boxes. Those are transformers. So they send out the electricity hundreds of thousands of volts, but what goes into your house is only 120. So there was a lot of upside to the AC, and obviously that's the one that won. You can do this with there's this app here, Arduino Science Journal. There's a bunch of apps, physics apps, but you can get one of the sensors on your phone picks up magnetic fields, and charges put out magnetic field. They put out electric fields, but they also put out magnetic fields. So you can put it, if you put the phone near a DC, like your charger, the side of the charger that comes out of the box that goes into your computer, that'll just show a steady magnetic field. It won't really fluctuate. If you put it on the other side, the power side that's coming out of the wall before it gets to the transformer, it'll fluctuate up and down. And then you can see AC versus DC. The lab will come back to. All right, so what causes charges to move is what we call voltage. It's a capital V. Lowercase v is velocity. Uppercase capital V is voltage. And all it means, and there's a bunch of words for voltage, but it's an electric potential. So you have this electric potential difference between 2 points. So up here, we have a high potential, and then at the bottom here, we have a low potential. The charges so the battery is going to pump them up to high potential, and then they naturally fall down to low potential. And we can take advantage of that. While they fall, this R is representing a resistor. It's going to take some of the energy out of the circuit. It doesn't take charges out. The charges are in the material. Like, you can't take those out, but you can take energy from them. And again, they don't really flow. Charges don't really flow like this. It's more of a jostling, not this flow that we kind of envision. But this, you can think of it that way. You'll get the right answer. It's just not really happening that way. But all right, the potential difference between is here. When we get to electromagnetism, we'll talk more about this. But what happens is when you hook up the battery, it produces an electric field, and that field covers the whole circuit. And so that's why when you turn on a light switch, the lights pretty much turn right on, right? There's maybe like a split delay, but we're not talking anything noticeable. So it's not that the energy has to flow through each electron. It's that back here it produces, and we'll talk more about this later, but we're getting into stuff we haven't talked about. But back to voltage. It can be thought of as a push that moves the electrons. Like that's what you're visualizing. And it has to have and it will naturally flow from high to low. So this little silly bird over here is safe. If you're just on the high side or the low side, you're fine. You could be up here, you could be down here, you're fine. It's when this bird stretches out its wings, here's one wire that's low or high, and here's another wire that's the opposite. Then you have a problem because the charges are going to flow through you to get to the low side. And again, they're not actually flowing, but they are. There is some motion here. The Van de Graaff generator, sorry, I can't. Yeah, it's another video. Look up Van de Graaff generators. There's some cool demos on them. But they just build up a bunch of charges. And then I just show it at this point for showing you that charges go from a high potential to a low potential. And then that's how the Van de Graaff's shocking people. Now describing voltage. Like I said, there's a bunch of ways to describe it. Potential energy is not voltage. So we talked about energy, potential energy, storage energy. We talked about gravitational storage and spring storage. This is electric storage, electric potential energy. So batteries push charges to a higher potential energy. And then the voltage is the energy per charge. So yeah, the battery's giving it more energy, And then what we call that energy per charge is voltage. It's not just energy, it's energy per charge. So that's potential energy. Potential, or if it just says potential or potential difference, that's voltage. And then that is just difference in voltage between 2 points. So if you just pick 2 points on the circuit, we call that a potential or potential difference. That's voltage. Electromotive force is also voltage. It's EMF. It's the Greek letter epsilon. It's specifically the potential across a battery or a generator, whatever's providing the power. So in this picture, what is being measured in the image is, you could call it potential or potential difference, but in this case, it's electromotive force. They would be referring to the EMF of that battery. I'm not going to be that picky about it, but just so it's in the back of your head. What is the voltage across the light bulb when closed? Well, if this is 1.5 volts and this is just a straightforward circuit, this light bulb is also going to get 1.5 volts. So it starts at a positive 1.5 and then it's got to end up at 0 by the time it gets back. So this thing has to take all the voltage, and we'll talk more about that. Some more voltage sources, just batteries versus generators real quick. Again, batteries are going to push charges through a chemical reaction. And then generators are actually pushing it through the turning of a wire. And again, that's electromagnetism. We're getting there. Both require energy to push the charges. And then you don't run out of charges, you run out of energy. The charges are always in the wire, or the charges are always in the chemicals of the battery. You don't run out of charges, you run out of energy. And then this image is just showing a charging process. So it's discharging. The charges naturally flow, and then you got to push them back, right? The charges are going to naturally flow to their opposites attract. So the positive are going to flow to the positive, the negatives are going to flow to the negative, and we can take that energy and use it. Now to charge it, then we got to push back, and that's what, when you plug it into the wall, that's what you're charging there. So we charge it, there's charging, and then here's discharging, and they just naturally flow. So that's voltage sources. How does a light bulb node on determine? And then here's our, I call it a flash forward. Again, I can't show you the video, but if when we get to electromagnetism, we'll talk about fields and how the charges actually move. It's not like all the images I've shown you so far. It looks like it's flow, like you turn on water. A lot of the analogies look like that, and you can think about it that way, but it's not really happening that way. But with that, again, we'll talk about fields when we get to electromagnetism. Resistance. And then electromagnetism, it's a combination of electricity, which we're starting here, and then magnetism. This is specific to circuits, though, at the present time. So resistance is a capital R. Lowercase r is usually radius. Not that capital R can't also be radius, but in this case, this capital R is resistance. But measure of how fast an object resists, I'm sorry, not how fast, how much an object resists the current. And then it's measured in ohms. It's the Greek letter omega. It's volts per amp. And so you can write out ohms, or you can make this horseshoe looking Greek letter. Everything has some resistance, and then that's what this equation's given us. So R is the resistance. Resistors, sorry, little side thing, look like these guys. If you've ever opened up some simple, well, any circuit usually has some type of resistor. The colors are coded to give you the resistance. If you don't have a multimeter and you know the colors, you can look up how much resistance is on it. And then this is the squiggly lines here, the schematic for it. So that's how we represent a resistor, is with the squiggly lines. But so here, insulators have high resistivity. That's what rho is. This is the Greek letter rho right here. That's the resistivity, and then that would be a value we would look up. Conductors have low resistivity. So if you want a low resistance, you're going to use something with a low resistivity. So here we got, oh, here, hold on. Measures resistance of variable, oh, that's a demo, sorry. Well, here, I'll explain the demo. The length. So how do you get resistance? It's this resistivity value we'll talk about in a second here. And then it's just the length of the wire over the area. So if you have a really thin wire, you're going to get a really big resistance, because the smaller this, right, this is denominator, the smaller the wire gets, the thinner the wire gets, I should say, is the resistance increases. Now, instead of messing with the area, if you had 2 equal areas of wire, you could increase the length. So if you take a longer piece of wire versus a shorter piece of wire, you're going to also have more resistance in the longer wire. That's what the L is there. All right, and then resistivity. So again, the lower the resistivity, the lower resistance. So silver is 1.59 times 10 to the negative 8. So why don't we use silver for our wires? Why do we use copper? It's 1.68, right? 1.68, 1.59. Silver has a better resistivity for low resistance. And it's not that we can't use silver, but you wouldn't want it. It's expensive, so you wouldn't want to put it throughout your house. And then so we ended up using, same with gold. It's expensive, so we went a lot of wires copper, but there's also aluminum wire. Um, and then gold. Sometimes you'll see stuff that's gold plated. It has a low resistivity